Hello, everyone. Welcome to another wonderful day of chemistry. So today we're going to be looking at radioactive cascades. So the big idea here is that it turns out, as we kind of started to see last time with uranium, lots of nuclei don't undergo a single radioactive event. They tend to occur in sequence, one after another, till somebody becomes more and more stable. So one of the big things that is worth noting is that nature is full of a whole bunch of nuclei that essentially can exist for fairly long times before decaying, and then may end up producing other nuclei that can exist for other long periods of time. So we're going to go ahead and look at these events. So one of the first things I want you to keep in mind is the heaviest element that occurs naturally is bismuth 209. So this is the last stable element. There are other elements that occur naturally, but they will break down in time. If you ever see an atomic number higher than 209 or a nuclear number higher than 83, know that it won't last forever. However, once you get to bismuth, you're good. Anything past this will only be semi-stable, and the real question is not if it will break down, but when. And one of the things is that a lot of these elements exist way beyond 83, and so they can't form a stable nuclei via a single event. So many of them will release a large series of alpha and beta particles, reducing the size one at a time until you form something stable. These combined events are what we call a radioactive cascade. The most famous example is U-238. Uranium-238 is the most abundant isotope of uranium. It occurs in relatively high abundance, and it can go ahead and break down to form an isotope of lead. And so it's worth noting that U-238 does possess the highest both atomic number and mass number. You know, if you have an atomic number higher than 92, that this is a man-made element. These are called the transuranics, and we'll talk about them later. Similarly, if you have any mass number higher than 238, you also know that it is a man-made element. So what we're going to be looking at is a 14-step process by which U-238 will form lead-206. Now, lead-206 is a really good island of stability in terms of nuclear structure. It has a double set of magic numbers, 82 with 82 protons and 124 neutrons. So this decay event is going to involve the loss of 10 protons and 22 neutrons. So this is quite a long way to travel in terms of structure. That is a full 32 nucleons we're going to lose. And this process is known as the uranium series. So let's go ahead and get started. We've already seen the first event of the uranium series. It's an alpha decay from U-238 to thorium-234. Releasing an alpha particle, also known as a helium atom. From here, thorium can undergo a sequence of beta decays. So again, this is a release of high energy electrons to first form proactinium and then reform our uranium. Again, this time we have had 3 events and have lost 4 net neutrons. However, it is worth noting what we've actually lost is 2 protons, 4 electrons, and 2 neutrons, and 2 electrons. From here, the uranium can then redecay back into thorium, but now thorium-230 via an alpha decay, then another alpha decay to radium-226. This also is a semi-stable species and gives this series the name of the radium series. And it is worth noting that Marie Curie originally was able to isolate radium out of uranium ore. And one of the reasons why it was so noticeable is that radium is slightly more reactive than uranium, so it actually decays at much more measurable timescales. This radium can then decay into radon. Yes, this is the radioactive gas that is found in many old buildings via another alpha decay. And then radon goes down to polonium. Again, polonium-218 via a 5th fifth alpha decay. So we've now had 5 alpha decays and 2 betas. Once we get to polonium, though, many different decay routes are available. Some include gamma radiation, but we're going to go ahead and look at the most common route. So the most common one involves polonium going down to form lead 214. From here, we then undergo a sequence of 2 beta decays to reform polonium again, but do note now that we have polonium 214. So again, we drop the mass of 4. Then we have another alpha decay, followed by 2 more beta decays, again, reforming polonium. So we're keep on going back and forth in between polonium and lead, stopping at bismuth several times along the way. And then we have a final alpha decay to generate lead 206. So this is the major idea of this series. What we're essentially doing is every one of these molecules is both a little too heavy, and sometimes a ratio goes a little bit too neutron heavy, as I'm releasing equal amounts of protons and neutrons. So I need to go ahead and turn some of those neutrons back into positrons to get to protons to get a little bit better balance. And this is where we often see these paired alpha and beta decays, as we both need to get my mass down, but keep a good ratio of protons to neutrons. So next time, we're going to go ahead and look at this series again, but with a little bit more focus on exactly how long these decay events take. Until then, take care.